Welcome to This Explainer. Right off the bat, we're going completely off the beaten path today. I mean, forget everything you know about standard benchmark scores or those simple pass or fail tests. Instead, I want you to picture AI safety as an epic, intricate journey across a sprawling map. Our guide for this? A fascinating piece of research detailing something called the boundary transition model. This framework is a real game changer because it forces us to stop looking at AI models in isolation and start looking at the actual messy environments we unleash them into. Okay, let's dive into this with a question that sits at the very heart of this explainer. If an AI passes a safety test, is it actually safe? Kind of feels like a trick question, right? But it's the central mystery we're going to unravel today. You see, when we say an AI passed, we usually just mean it gave a safe, harmless answer to a specific prompt. But out in the wild, a deployed AI isn't just answering a single prompt in a vacuum. It is actively navigating complex, multi-step digital environments. To really grasp why that matters, we have to look at two entirely different ways of evaluating risk. The old paradigm, output-only evaluation, well, it's kind of like testing an explorer's ability to take a single isolated step. Sure, they didn't trip, but that tells us literally nothing about where they're actually heading. The new reality, it demands end-to-end boundary evaluation. Real-world failures almost never happen in one isolated step. Our AI Explorer has to make sustained progress, using tools and bypassing guardrails. We absolutely have to evaluate the entire sequential journey, not just that first step out the door. Section 1. The Explorer's Journey, Navigating the Boundary Graph. Let's get into it. So imagine a deployed AI system, not as this static brain in a jar, but as an explorer dropped into a complex, dark labyrinth of digital workflows. To map this labyrinth, researchers created the Boundary Transition Model, or BTM for short. Conceptually, I want you to picture a digital map with these glowing paths connecting different nodes. Some of those paths represent normal progress, while others lead straight to a designated boundary, like a critical edge of the map that we absolutely do not want crossed. The BTM tracks the exact probability that our AI Explorer, operating in the real world, will navigate this glowing network and actually stumble into that dangerous terminal state. But, our Explorer isn't traveling light. Their deployed configuration is essentially their survival gear. Step 1 is the base model, right? The raw neural weights. But modern AI carries so much more. Step 2, we have tools like web search or code execution. Step 3 is a routing policy to guide its decisions. And step 4, retry and recovery mechanisms. The critical insight here is that an AI's safety profile radically changes based on this equipment. You can literally have the exact same base model, but the second you hand it a new tool or a retry loop, its ability to cross a dangerous boundary on the map completely transforms. Section 2. Bridges, loops, and bottlenecks. Let's look a little closer at the map itself. Just like a physical landscape has mountains and valleys, your digital workflows have 3 distinct geographic features our AI Explorer is going to face. First up, horizon decay. Basically, the longer the trek, the harder it is to survive. Second, bottlenecks. Think of these as narrow bridges or mandatory mountain passes. In your company's workflow, this might be a triage queue or a database where a human actually has to approve an action. Every single path to danger has to cross right here. And third, retry loops. These act like extra rations, letting the AI just brush itself off and try a failed path again. It multiplies their persistence without them actually getting any smarter. Let's look at the hard math of horizon decay. If our AI has to take a long journey of 15 steps, the probability of it crossing a dangerous boundary drops all the way down to just 0.0299. Now compare that to taking just a single step, where the probability was a massive 0.6452. To put that into perspective, that is a huge drop. It beautifully illustrates that distance itself is a safety measure. That multiplicative exposure to failure naturally degrades the AI's ability to cross a boundary. Basically, the longer the journey, the safer we are, even if the AI's step-by-step intelligence remains exactly the same. But what happens when we hand our Explorer a new tool? If we just make the AI generally smarter, a broad local improvement, its chance of crossing a bottleneck sits at about 0.2360. But give it a specific tool, suddenly, that crossing probability jumps to 0.4210. Why? Well, because you didn't just make the Explorer smarter. Actually, scratch that, it's more like you unlocked a hidden bypass edge right around the mountain. You fundamentally altered the terrain itself. Now, what's really interesting about this slide is the hidden danger of retries. If you give the system wrapper an 80% retry loop, the probability of crossing a dangerous boundary skyrockets to 0.6310. Think about that for a second. The base AI didn't learn anything new. It didn't get better at reasoning. But simply adding a silent background retry loop turns what should be a temporary stumble into a relentless siege on the boundary graph.
Section 3. When safe modules combine, the non-additive twist.
This brings us to a real climax in our journey today. What happens when seemingly harmless tools interact? Well, if we test a planner module in total isolation, its boundary crossing probability is exactly 0, perfectly safe. If we test a tool module in isolation, it's also 0. But equip our AI Explorer with both the planner and the tool simultaneously, the crossing probability explodes to 0.7785. That's right, 2 perfectly safe pieces of gear just unlocked a complete, highly dangerous path the second they were combined. I just want to let this quote from the researchers sink in for a moment. The risk is not the sum of independent module risks. It is generated by a path that becomes traversable only when modules interact. This is profound. It mathematically proves that you absolutely cannot test AI modules in isolation. If you want to understand the true risk, you have to map the complete journey. Measuring the parts will never, ever give you the danger of the whole. And listen, this isn't just theoretical math. The researchers applied this to a real-world retail agent benchmark. Across 25 tasks, the AI had a pretty moderate average success rate. But looking under the surface, 8 tasks were always solved, and 9 always failed. The AI's capabilities exist in these stable, hidden regimes. A simple average score completely masks this extreme task-level heterogeneity. Averages hide the actual shape of the map, blurring over the specific routes where the AI operates with total success or just fails completely.
Section 4. Controlling the deployment terrain.
We've mapped the labyrinth, right? So now, how do we control it? And this brilliantly illustrates the mathematical solution. If you use a uniform maximal release, meaning just letting the AI loose everywhere, you get a net objective of 2.793, but a massive boundary risk of 4.305. However, if you use a revocable tiered release, where you assign capabilities only to trusted environments where you can easily revoke access, the risk plummets to just 1.187. Residual harm drops to nearly 0, and the net objective actually rises to 3.090. The math proves it for sure. A strategic, tiered rollout is vastly superior to just turning the AI loose. So, the crucial point is that AI safety isn't just about tweaking the AI's internal brain. It's about deliberately architecting the map it operates on. We have tangible control levers here. We can remove edges from the graph. We can constrain tools so those sneaky bypasses never appear. We can reduce retry budgets to kill persistence. We can harden those narrow mountain passes, those cut-set bottlenecks, and we can absolutely restrict module composition to prevent those non-additive jumps in risk. These are real, structural interventions. This completely shifts our perspective, and it's perfectly captured by this quote. Release becomes an allocation problem rather than a binary decision. We have to stop asking simply if an AI is safe to deploy. The real question is where it is safe to deploy, under what environmental controls, and with what capacity for revocation if it starts crossing boundaries it really shouldn't. Which brings us to the end of our journey today and leaves us with one haunting question to ask ourselves and our organizations. Are you just testing your AI's first step, or have you mapped its entire journey? The boundary transition model proves that local safety does not equal global safety. The map matters, the tools matter, the terrain matters. It is definitely time we start evaluating AI not just for the output of a single prompt, but for the entire end-to-end journey it takes through our digital world.